This is Natalie. She will be giving us a talk on last week's lab, the thermocouple time constant experiment.
I'm Natalie, and I was the reporter for Group 1, and I'm going to go over the results of our thermocouple time constant experiment. A thermocouple is a temperature probe that is made of dissimilar wire legs that are welded together to create a junction at the end of the probe. When the junction is inserted where there's a temperature change, a voltage is created that the data acquisition that's used can create back to the temperature. This is done because the rate at which the thermocouple sensor exchanges heat with its environment equals the rate of change of the internal energy. Our objective was to graphically determine the thermocouple time constant from the transient response of our thermocouple probe when it was inserted and removed into boiling water in an ice bath. In our case, our group did the ice bath. The time constant is the time required for the temperature to reach its final temperature, for about 63% of its final temperature being subjected to an instantaneous temperature change. The time constant can be affected by size or the medium that it is being placed in. As for air and water, there's a different time constant, and also still air and moving air has different time constants. Our case, we used the lump capacitance method. We were able to use this because the objects were being cooled or warmed uniformly under the influence of convective cooling and warming. When you use the lump capacitance method, it assumes that there's no temperature gradients within the medium. Also, the energy balance equation has the rate of energy that is convected to or from on the left side and the change in thermal energy on the right side. When you integrate that equation with initial conditions, you get the equation on the bottom, which substitutes the time constant as tau into the equation. Our testing apparatus included a 50 milliliter flask full of boiling water or an ice bath, hot plate heater for boiling water, type K thermocouple, paper towels, and a computer system with the PDAC acquisition. Our procedure for the ice bath insertion test was to make sure that the thermocouple was at room temperature and then plunge quickly into the ice bath. Once the temperature stabilized to the ambient temperature of the water, then the data was stopped being logged. Procedure for the removal test was to begin with it inserted in the ice bath until it reached the temperature of the ice bath, and then to start logging data and then take it out, dry it off with a paper towel, and hold it still in the air until the temperature stabilized. It must be dried off because you have to make sure that the immediate surroundings around the probe are the ambient temperature of the air and not the water. And then it must be held still because if you move it around, it would have different time constant. It would be shorter than if you hold it still. So we began with the insertion, and the raw data was taken. It was taken at 5 hertz, and it took about 23 seconds to stabilize. The raw data can be seen right there, and then the data was normalized using that equation with T being temperature at time T. T infinity was the temperature, the final temperature, which was the temperature of the ice bath, and it was 2.51 degrees Celsius. T0 was the temperature at 0 seconds, which in this case was the ambient air temperature at 23.3 degrees Celsius. Once we had the normalized temperatures, the natural log of that was then taken in order for the plot to model the energy balance equation, which can be shown right there. So when it was, the log was plotted versus time, you can see that the time constant became the slope of the equation. So linear fit was taken, and the slope of that was equal to the time constant. And for the insertion, it was about 4 seconds. For the removal, the same thing was done, but it was taken at 3 hertz frequency, and it took about 225 seconds to stabilize. So the data shows there, and then the data was normalized again, with T infinity being the temperature of the air this time at 21, and T0 was the temperature of the water at 2.6 degrees Celsius. When the natural log of that was taken, the time constant was once again the slope of the linear fit, and this time was 64.17 seconds, which is much larger than the insertion. The data that we compared it to was the boiling water, and the boiling water insertion time constant was 0.7 seconds, which is a lot quicker than the ice bath. And the removal time constant was 62 seconds, which is comparable to what we got for the ice bath. Some conclusions are that the time constant is much larger when being removed from the ice bath than when being inserted, because the thermocouple responds much slower in air than water, and this can be due to different material properties, such as the specific heat of air versus the specific heat of water, or the density. And so that's why it took a lot longer to stabilize in the air than it did in the water.